Okay, so let's get started. This is gonna be the 9th lecture. And maybe let me get started by reminding you what we talked about last time. So last time we talked a bit about reductions of second order differential equations to first order differential equations, both the explicit reduction method and the autonomous reduction method. We saw a couple of examples of that, and then we ended up talking about exact differential forms. That was the last thing that we mentioned. So maybe let me remind you a bit about that. So we start from an ODE. We start with an ODE of the form dy over dx is equal to f of xy, and we recast it in differential form. Recast it in differential form. So this is we write this equation as mxy dx plus nxy dy equals 0, where mxy and nxy are chosen so that f of xy is equal to minus m of x comma y over n of xy. This is sort of what we mentioned last time. What we said is that if we are lucky, there will exist an integral h of xy such that the x of hxy is mxy and dy of hxy is nxy. So this is exactly the definition of being an integral. This differential form has an integral h of xy if you can find this function hxy satisfying these two equations for their partials. And when this is the case, we say the differential form in star is exact. So here star is this differential form. Yeah, that's what we said last time, but we didn't talk really about how to. It seems for now that if you want to test if a differential form is exact, you should try to guess what h is. But there's actually a criterion for check exactness, and this is Euler's exactness test. And what this test says is the following. It's based on the simple observation, that partial derivatives commute, meaning that if you take partial x, partial y of hxy, this should be the same as partial y, partial x of hxy, as long as hxy is sufficiently differentiable. So, so we see that because an exact differential form has the structure up here, then an exact differential form must satisfy the following. So it must satisfy that the x of, well, what's dy? dy here is dy here, so that's nxy. The x of nxy should be equal to dy of what? Of mxy. Yeah. And that should be a necessary condition for the differential form to be exact. But what Euler showed is that it is actually sufficient. Euler showed that if R, this is the domain where hxy is defined, that's the notation we've been using. If R, the domain where hxy is defined, has no holes, then the converse holds too. Meaning, in the simplest case, suppose that you have this function hxy that's you have where actually I should say here where fxy is defined, that, or nxy or mxy, the same thing. That if you have this differential form with coefficients nxy and mxy defined in a region R, satisfying this equation over here, and moreover the region where they're defined has no holes, like it's not like all the plane but a little hole there, then it happens that this actually shows you that the form is exact, so they will exist an integral. And what we want to do now, basically, and what we'll do now is, instead of giving you a recipe or like a formula for figuring out what an integral is, we'll just do it by looking at an example. You notice that it's very sort of natural. Once you know that your form is exact, using Euler's exactness test, it's very easy to, or natural to come up with an integral. Yeah. So maybe let's do that next. So here is the example. So solve the initial value problem given by dy over dx plus e to the x y plus 2x over 2y plus e to the x is equal to 0, and y at 0 is 0. Yeah. So you can see, and maybe let me write solution here. You can see that this is quite a complicated ODE, and it seems kind of hard, at least by looking at it, to try to solve it with any of the methods that we've discussed up until now, because it doesn't seem easy to separate, it doesn't look linear, etc. So it's sort of complicated in that sense. But we're going to see that using this idea from Euler, we can find an integral and then solve this ODE. So let's see how to do it. So first let us cast this equation in differential form. So I just been writing it as something dx plus something dy equals 0, and by playing around with the arguments here, you can see that what you get is just e to the x y plus 2x dx plus 2y plus e to the x dy is equal to 0. And we have, let me also write the initial condition. So that's what you get when you recast the equation in differential form. Now, the first thing that when we have a differential form, the first thing that we should ask is if it is exact or not. So here's where we apply Euler's test. Applying Euler's test, what we have to do is take partial y of the first guy and compare it to partial x of the second guy and check if they're the same. So let's do that. So we do partial y of e to the x y plus 2x. Well, that's just e to the x. And then dx of the second guy is 2y plus e to the x, which is also e to the x. So what this means then is that Euler's test is satisfied. So the form is exact. So we're good. We at least know it's exact. So this means that thus, by Euler's criterion, there exists an integral h of xy such that what? Such that the x of hxy is equal to the m function here, to this m function. So maybe let's just say that to make it more clear, according to our notation, this guy here is m of xy, and this guy here is n of xy. So if there was an integral, what the definition says is that to be an integral, the partial of that integral with respect to x should be m of xy. So it should be e to the xy plus 2x. And at the same time, it also asks us for the partial with respect to y to be equal to n of xy. So to be equal to 2y plus e to the x. Yep. Okay, so now we want to know what this integral is from these two equations. So let us do it in the following way. So we consider the explicit equation, the first of these equations. So we consider the first equation, which is just partial of x hxy equals e to the xy plus 2x. So what we're gonna do is think of x as variable, because we're taking partials with respect to it, and y as a constant. So in that case, this is an explicit equation. You can see I just have the derivative of a function equals another function. So then as this is an explicit equation, what we can do is just integrate both sides. So integrating both sides, what we're gonna get is that h of xy is equal to what? The integral of this guy with respect to x. So what's the integral with respect to x? Well, it's ex y plus x squared plus a constant. But here we have to be a bit careful because y is a constant. So a priori, this constant here could depend on y, and we should be all together in the same situation. So because y is constant, what I should write instead of a generic constant c, I should write a constant of integration, which is a function depending on y. Yeah? Okay, so I do that. And now, so let me just write that where h of y represents the constant of integration. Okay, so now plugging this expression. So now what do we have? We have sort of an expression for hxy, but we still want to sort out what this guy over here is. We don't know what hy is, but we still haven't used the second equation over here. So to figure out what hy is, we're gonna take this guy and plugging into the second equation and see what we get. So plugging into the second equation, well, what do we get on the left-hand side? Well, we get the partial with respect to y of hxy. And what's that? Well, it should be e to the x. X squared doesn't depend on y, so it gives us 0 plus h prime of y. And on the other hand, I get 2y plus e to the x. So what this is telling me then is that h prime of y is equal to 2y. And now this is an equation that we can solve and just say that h of y is equal to y squared. Yeah. So at the end of the day, so we thus have that h of xy is equal to e to the x. So let's go back up. So it's equal to e to the xy plus x squared plus h of y, which is down here. So it's e to the xy plus x squared plus y squared. So we're good. And but we still haven't finished because this is an initial value problem. So what we're looking for, we look for a constant c. So maybe let me say we look for a level set of the form e to the h xy equals c, which gives us the solution to our initial value problem. So what we should do is just we plug in the initial condition as always. When we want to sort a constant, we plug in the initial condition that y at 0 is 0. And here what you should think about is that this 0 here is the x variable. Yeah, because y is a function of x, y at 0 is 0, so that's what happens. So then let's plug in this initial condition, and we're gonna get that h of what? H of 0, comma 0 is, because x is equal to 0, y is equal to 0, and this should be equal to c. But what is h of 0, comma 0? This is just, well, you look at the thing up top here and plug in zeros everywhere, and you see that it's 0. Yeah. So c is equal to 0. Yeah. So if c is equal to 0, therefore, it follows that our solution satisfies h of xy is equal to 0. But what is that? That's just e to the xy plus x squared plus y squared equals to 0. Yeah. And this would be an implicit equation, but notice that this is a quadratic equation for y. So if you just applying the quadratic formula, you just get that y is equal to minus e to the x plus minus square root of e to the 2x minus 4x over 2. Yeah. Now this may seem weird because we're looking for the unique solution, but we have a plus minus, but the initial condition forces us to, because the initial condition is 0, that forces us to pick the solution with a plus sign, because that's the only way you're going to get a 0. Yeah, if you pick the solution with a minus sign, you're not going to get a 0 as your initial condition. And to be 100% clear, we should say that this is defined whenever the thing inside the square root is positive. So whenever e to the 2x minus 4x is positive. Yeah. 4x squared, sorry. This should be 4x squared. I missed something here. Yeah, 4x squared. 4x squared, that was a mistake on my part. Okay, so let me make a few remarks. The first remark that I want to make is that instead of starting from this equation over here and integrating this equation and then plugging in back here, you could have perfectly started from this equation over here, integrated this equation with respect to y, and then plugging it into the first equation to figure out the constant of integration. That's also perfectly fine. And in some cases, it turns out that the order in which you do these things, it never changes the answer, but sometimes one of them is way easier to carry out because the integrals are easier. So just keep that in mind, that for certain problems, it might be actually easier to integrate the equation with respect to the partial of y, and then plug it into the equation with the partial with respect to x, just because the integrals that show up will be easier. Yeah, that's one comment. And the second comment that I want to make is that this procedure that we just described can be turned into a general theory, but just because I prefer you focusing on the method, we won't cover that in class, and in some sense, it's just more practical to know how to directly apply this idea in exercises. It's always the same idea. You check, so maybe let's do a little recap. You're given a differential form. You want to solve the corresponding differential equation. First thing you ask, is the form exact? You apply Euler's test and you check that it's exact. Once it's exact, you set up the equations that would define the integral, meaning these two equations over here. And once you have that, you solve those two equations by first integrating one and then plugging into the other in whichever order is more convenient. Yeah, that's what we just mentioned. Okay, so the last thing that we're going to cover is just what happens when the form isn't exact. So that's something that we'll use a certain technique. So maybe let's call it integrating factors. And the situation is the following. Suppose we had a differential form mxy dx plus nxy dy, and let's say we're trying to solve the equation where this is 0. And let's suppose that this form is not exact. So the question is, what shall we do then? Because we mentioned that it's sort of not the easiest thing in the world to be exact. So what shall we do if our form is not exact? Well, what we can try to do is try to turn it into an exact form by multiplying it by something. So notice that if rho of xy is not 0, then the above equation is equivalent to multiplying the whole equation by rho xy. So it's equivalent to rho xy mxy dx plus rho xy nxy dy equals 0. So what we should do then is seek rho of xy such that this form is exact. i.e., such that it satisfies Euler's exactness criterion. That means that dy of rho xy mxy equals dx of rho xy nxy. Okay, so that's what we're gonna do. And okay, so maybe let's do one more step here. So applying the product rule, we'll get that, we'll get dy of mxy rho xy plus dy of rho xy mxy equals dx nxy rho xy plus dx rho xy nxy. Yeah, we get an equation which is kind of complicated, and we're trying to look for a rho that satisfies this equation. So it seems that we've gained nothing, but it's useful. It is useful to try to solve this equation. Assuming either that the function rho, its derivative with respect to x is 0, or that its derivative with respect to y is 0. Yeah, it turns out that in many cases, if you make this assumption, you're still able to get a solution. And notice here that when we're looking for rho, we're not looking for the most general rho that would solve this equation. We're just looking for a single one. If we get a single one, we're good. So that's what we're gonna do. We're gonna look for a single one. And when we look for it, we're allowed to make extra assumptions to make our problem easier. And the assumptions that we'll usually make is that the partial with respect to x is 0, or the partial with respect to y is 0. So I could go on with the more general theory, but let's just see how this works in an example, and you'll see what I mean. Let us see this in action. So consider the following example. So find an implicit solution to the differential equation two e to the x plus y cubed dx plus 3y squared dy equals 0. Yeah, we're given this differential form and we're asked to solve the differential equation. So as always, the first thing when you're given a differential form and an equation written as a differential form equals to 0, the first thing we always do is check if the form is exact. Okay, so maybe let's start writing the solution down here. Solution. So first, check if exact. So for that, we apply Euler's test. So that would tell us that the x of the n function, so we compute the x of the n function and the y of the m function. So let's just do that. The x of nxy, that's equal to the x of 3y squared, which is equal to 0, because there's no x there. And then the y of mxy, which in this case equal to the y of 2e to the x plus y cubed. So this is 3y squared. Okay, so you just see that these two partials do not agree. So that tells us that the form is not exact. Okay, kind of a bummer. But what we know is that we can apply this integrating factor technique to try to make it exact. So we look for an integrating factor for rho xy such that, well, let's multiply everything by rho xy. So 2e to the x plus y cubed rho xy dx plus 3y squared rho xy dy is exact. That's what we're gonna look for that, for a row that does this job. So good, that's what we're gonna look for. So for this to be exact, so then by Euler's criterion, we should have that partial y of the m function, which in this case is 2e to the x plus y cubed rho xy, should be equal to partial x of the n function, which in this case is 3y squared rho xy. Yeah, so let's apply the product rule. So by the product rule, this is the same as, well, let's try to do it. Okay, I should write square parentheses here to make it more clear. Okay, partial y of this guy is 3y squared, 3y squared rho xy plus 2e to the x plus y cubed rho xy, partial y of rho xy equals to, well, the x of 3y squared is 0, so nothing there, and then 3y squared partial x of rho xy. Yeah, I just expressed everything after using the product rule. And the question is, what is better? What is better to assume? Do we want to assume that dx rho is 0 or dy rho is 0? Well, if we look at this expression here, it would seem that if I assume that dy rho is 0, this whole complicated thing will vanish, and then I'll get a very simple expression for rho xy. Yeah? It seems like I made have I made a mistake? No, I'm good. Yeah. Okay, so we're good. And as I said, it seems like in this case, it's easier to assume this condition. Yeah, so that wins. And then assuming this, we get that 3y squared rho is equal to, well, the second thing just vanishes. This thing just vanishes completely. And then we get 3y squared dx rho. Okay, so let's cancel out the 3y squareds, and then we get dx rho equals rho, which is a very simple equation. And we just need to find one solution to this. I don't care about the most general solution. I just need to find one. So I'll just say, so we take, so this is the usual equation satisfied by exponentials. But if it was something a bit more complicated, you would have to integrate something more complicated. But we're just going to take rho equals to e to the x. Yeah, that's enough. And as rho is the integrating factor, we get an exact form, our form that we constructed by multiplying by rho. So this form over here, this guy over here, this form over here will now be exact. So let me just write it down. So this is 2 e to the x plus y cubed e to the x. That's what this guy is here. The x plus 3y squared e to the x dy. Yeah? Okay, so now we have an exact form, and we're trying to solve this ODE. As this form is exact, so we're trying to solve that ODE. So this form is exact, we can proceed as before. As in the previous example. So let's do it once more, just as practice. So what do? So we look for an integral hxy such that what? Such that this is the integral of this differential form. So that means that the x of hxy is equal to mxy. So that's just 2 e to the x plus y cubed e to the x. And we also want the partial of hxy with respect to y to be equal to nxy. So to be equal to 3y squared e to the x. Yeah. In this case, as we said before, now we need to choose one equation to integrate. And the second equation looks much simpler, so let's do that. So integrating the second equation, grading the second equation with respect to y. to y, considering x as a constant, what do we get? So we get hxy is equal to y cubed e to the x. So x here is a constant, so e to the x is a constant, and the integral of 3y squared is y cubed. Now you would write this, but as always, you need to consider a constant of integration. So you would write a constant here. But now it turns out, I'm just reviewing what we did before, that x is also considered as a constant. So your constant can also depend on x, so we usually write it as h of x. So we know that capital H of xy should be y cubed e to the x plus some function of x. How to figure out that function? We go back and plug in into the first equation, into the other equation, which in this case would be the first one. So plugging into the first equation, we get, okay, let's plug into the first equation. So the first equation is this one here. So what we would get is, well, let's consider the partial of hxy. That's y cubed e to the x plus h prime x. That should be equal to 2 e to the x plus y cubed e to the x. And then from this, just simplifying out, you see the y cubed e to the x simplified. So you just get that h prime x is equal to 2 e to the 2x. And now you just need to solve that. And the way you solve that is just, well, you integrate both sides and you end up noticing that h of x is just, well, e to the 2x, so that the constant in front is the right one. Yeah. So what do we conclude? So we conclude that that h of xy is equal to y cubed e to the x plus little h of x, which is e to the 2x. And then to finish, so this tells us that, so the implicit solution is given by setting h of xy equals to a constant, but that's the same as saying y cubed e to the x plus e to the 2x equals a constant. And that would be enough in this case because we're only being asked by the implicit solution. But just to make a comment more explicitly, you can also solve this thing for y. And you would get that y is equal to the cube root of c e to the minus x minus e to the x if you solve the equation. Yeah, but in this case we were being asked by an implicit solution, so this would be enough of a good answer. Yeah. Okay, so then let me recap what we just did. So you might be given an equation in, you might be given a differential equation in this form or in this form like here that looks weird, or more usually you're given directly a differential form like in this second example. And what you're trying to do is solve the corresponding ODE. What happens is that if the form was exact, then we know a procedure of how to solve it. So what you always do first is check if the form is exact. For that, you use Euler's criterion, which we described up here. Yeah, so Euler's criterion is this thing over here. You check that these cross partials match up. If they match up, your form is exact. If your form is exact, then you look for an integral, and looking for an integral means trying to satisfy these equations. So you get these two equations with partial derivatives, and to solve the equation, you integrate one of the equations and plug it into the other equation to figure out the constant of integration as we did below. And if you do that procedure correctly, and this is something that you should practice a few times, you will end up getting an implicit solution. Now, what's more common is that if you're given a form, that form will not be exact. So what will you do when the form is not exact? You will look for an integrating factor. So an integrating factor is this row such that this new form is exact. So you multiply everything by this row, and then you ask, is this new form exact? Well, how do you know? Well, you apply Euler's criterion, and you get this equation. Now, this equation, after you apply the product rule, becomes a little messy, like this thing below, but it happens that if you either assume that the partial of rho with respect to x or the partial of rho with respect to y is 0, then the equation usually simplifies a lot. So that's what you're going to do. You're going to make one of those two assumptions, and then you're going to get an equation for rho as we did down here. So maybe to highlight in this example, we chose dy of rho to be 0, and then the equation became this very simple equation, d of x rho equals rho. From that, you found the integrating factor, and that let you update your differential form to this new form, which is exact. So now you're in business. You have an exact form, and now you know how to find the implicit solution. What do? You just set up the equations of being an exact form, the ones that we mentioned in the beginning. These two equations over here. And as before, you solve one of them by integrating with respect to the differentiating variable and consider the other variable as a constant. And that will give you an hxy, which is almost determined, but it has this little function representing a constant of derivation, which could depend with respect to a constant variable. And to solve what's that function, you plug it into your second equation. Yeah. So that summarizes everything that we did. Okay, so then let me just mention that the next class in this series of lectures will be a review for the midterm, because this covers all the first big chapter of what we wanted to discuss, which are first order ODEs. And then the class after that will discuss a bit of linear algebra that we will need to know to deal with higher order ODEs. But for the midterm, you need to know what is in all previous lectures, what is in this lecture, and I encourage you to look at the review, at least to have some sort of checklist that you know everything that will be relevant there. Yeah, but with that, this ends the lecture of today.